Hello everyone, we're going to be doing our Chapter 7 review today. So we're going to start with section 7.1. 7.1 is definitely the largest chapter in terms of definition, terminology, so it's really important to know the terminology going forward because everything we see in Chapter 7 is really going to build on top of section 7.1. All right, so to start, we say that a set is a well-defined collection of objects in which it is possible to determine if a given object is included in the collection. So your set is just a defined collection. Sets often contain numbers, which are known as the elements or members of the set. So when we see this being written, if we let S be our set, then we see our elements are contained within our curly braces, so our curly parentheses that we see here. The elements don't necessarily have to be numbers. Your elements are just anything contained within the set. It's just that we will most often see them as numbers. To signify an element is contained in a set, we write this symbol here. It kind of looks like a euro symbol, but it's basically just a C with a line straight through the middle. And then to show an element is not in a set, it's the same symbol, just with a line through it. So it's that C, the line in the middle, and then a dash. It's possible to have a set with no elements, and this is called an empty set or the null set, and it's written as a 0 with a slash through it. So we see this symbol here. Whenever we write it, we don't want to write parentheses around it or have our curly brackets around it. We just want to write the one symbol, and that just means that there are no elements contained in that set. So really anything within a set is going to have elements, and there's literally nothing, not a 0, just nothing in the set, and the set is empty. So a word of caution to build on this, we see that the set of 0 or 0 within curly brackets and the non-empty set are two different sets. 0 is considered a number and is therefore an element. It is an element because it is inside of our curly braces, so therefore it is an element even though it is 0. It doesn't really matter what it is, it's just inside the set, so it's considered an element. While the empty set represents a set of 0 elements. All right, so we can use the symbol n of A, if we say the set is A, to indicate the number of unique elements in the finite set of A. So just the n with parentheses, we can have any set be called any variable, but that n parentheses within a set, we use that to indicate the number of unique elements inside a finite set. This is going to be very important moving forward, so remember that. Two sets are equal if they contain the same exact elements, so the ordering of sets doesn't matter, and we also see that each element is only listed once. So you won't have the same number listed multiple times since it's not unique. You'll just have it listed once, and then ordering doesn't matter. Sometimes we are interested in a common property of the elements in the set instead of the list of elements. So we use what's called a set builder notation. So we would say that X is all of our elements. So X is essentially the list of elements, and then we say that X has the property P. So when we write this, we have our curly brace, and then we have X, and then we just have a straight line, and then we have X has property P with ending curly brace. So that's just to say that if we want all the numbers between 0 and 1, we would say X and then our straight line and say X is between 0 and 1. Then important properties of subsets are going to be that, well, the definition of a subset is set A is a subset of B, written as A, and then we kind of see this sideways U with a line underneath. So that means that A is a subset of B if every element of A is also an element of B. Set A is a proper subset, written as A with just the sideways U, no underline, of B if A is a subset of B and A is not equal to B. All right, so subset properties we have for any set of A. The empty set is always contained or always a subset of A, and A is also a subset of A. This just means that You know, we can't prove that there's nothing inside of A, so we say that the empty set is an A. And then also, since every element of A is contained in A is a subset of A. So the number of subsets, a set of k distinct element has 2 to the power of k subsets. So this means that if you have a set that has 5 elements, that means you have 2 to the power of 5 subsets, or 32 subsets. Then we see here in figure 2 off to the side, this is called a Venn diagram. We'll use them to denote if an element is part of a set or not. So we can use Venn diagrams to just kind of visually picture this. And then we have important set operations. So we have the complement of a set. So we let A be any set with U representing the universal set. And then the complement of A, colored pink in this figure, is A, and we recognize that as A prime with an A apostrophe. So A prime is equal to X, where X is not in A, but X is in the universal set U. So that means that X is not in A, but it is in the universal set U, meaning that it is in complement of A. So remember that our rectangle represents our universal set U. Sometimes it's labeled and sometimes it's not, but if you have a rectangle outside of your circles, that just represents your universal set. All right, so when you're thinking of complement of a set, it's basically you're just thinking of anything that's not in the set. All right, so then we have intersection of two sets. So an intersection of sets A and B, shown in green in the figure below, is A intersect B is equal to X, where X is in A and X is in B. So we're looking for items that are in A and in B. Not just in A, not just in B, but it has to be A and B. When you see questions later on or word problems where you're asking for intersections of items, you're always going to see it be written as A and B, or something and something. So the word and is normally used for intersections. Then we have disjoint sets. So for any sets A and B, if A and B are disjoint sets, then A intersection with B is the empty set. And this, if we look here at figure 3, this is because when we write out our Venn diagram, we see that they don't overlap at all. They're completely separated. They don't share any elements. So if they don't share any elements, then the intersection will be the the empty set. Then lastly, we have the union of two sets. So a union of sets A and B, shown in the blue figure, or shown in blue in the figure below, is A union B is equal to X, where X is in A, or it's in B, or it's in both. So this means that when we have our two circles that are overlapping, it's just any region within the overlapping circles. So it's both, it's one or the other. When we see these written in word problems, you'll often see the word or. It'll be something or something. So whenever you see the word or, it usually means union. If you see the word and, it usually means intersection. And even though our union does contain the intersection, what we really want to find is if it's in one or the other, or sometimes both. So the word or is usually used for unions and is usually used for intersections. All right, on our first example, so we want to determine whether these statements are true or false. So we're just looking at these statements and deciding if they're true or if they're false. So for part A, we have 7 is in the set of X, where X is evenly divisible by 3. So this means that all of our elements in this set are going to be evenly divisible by 3. That just means that we don't have any decimals. So if we're saying that 7 is in this set, that means that 7 must be divisible by 3 evenly. But we know that 7 is not evenly divisible by 3, so this has to be false. So we say false. Oh, wrong color. False, since 7 is not divisible by 3. All right, so now for part B, we have a set of A, B, C, D, and E. And then we have that this is equal to 32 subsets. Well, we can use our equation for subsets, which was if you have k amount of elements, then you'll have 2 to the power of k subsets. So if we see here, we have 1, 2, 3, 4, 5 subsets. So this will be 2 to the 5th power, which we know is equal to 32. So this is true. All right, then for part C, we have the set of 1, 2, and 3, and then we have it intersected with the set of 4, 5, and 6, and we're saying that this is equal to the set of 1, 2, 3, 4, 5, and 6. Well, if we remember, the intersection is going to be counting the elements that are in both sets. Not one, not the other, but both. And if we see here, we have a set of 1, 2, and 3, and then we have a set of 4, 5, and 6. So they don't share any elements. So we say this is false, since either set, or since both sets don't share an element. And then we can say in parentheses, this would be true if we were taking the union. Because remember, in our union, it's what's in A, or what's in B, or what's in both. So when you take your union of things, you would combine them. So this would be technically correct if we were taking the union, but we weren't. We were taking the intersection. Another side note here, or here, we'll just add it on. So we say, this is false since both sets don't share an element, so it should equal the empty set. All right, so then on to example 2. We have find the following expressions using the given information. U is equal to the set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the values between 1 and 10. Then we have A is equal to the set of 1, 4, 7, 8, and 9. And B is the set of 2, 6, 7, 9, and 10. So we want to solve these following expressions. So for part A, we just want A intersection with B. So we're looking for the common elements, so the elements that these share. So we can say we see that both sets contain, and if we look here, we can look at A, which we see is 1, 4, 7, 8, 9, and B, which is 2, 6, 7, 9, 10. So if we're looking, we see 1 is in A, but not in B. 4 is in A, but not in B. 7 is in A, and 7 also is in B, so we can write that down. We see that both sets contain the number 7. Then we see 8 is in A, but it's not in B. 9 is in A, and it's in B. So we see that both sets contain the numbers 7 and 9. So we say they both contain 7 and 9. So when we write this, A intersect B is equal to the set of 7 and 9. Then for part B, we have A union B, but the complement of that. So what we really want to do first is we want to find the values inside the parentheses. It's just like how we usually do PEMDAS. You always want to start or backtrack. We want to start by finding A union B, and then it'll be easier to find the complement after that. Since we know our universal set, and if we find the union of A and B, then we know at the end which values will not be contained within our union. And then we can find the complement. So we want to do what's inside the parentheses first. So we have A union B. So if we take A union B, we know that this just means every element that's in A, every element that's in B, and every element that's in both. So we can just start writing values. So we see 1 is in A, and we want to write this in order. Just makes it easier. So we have 1 is in A, 2 is in B, 3 is not in either, 4 is in A, 5 is not in either, 6 is in B, 7 is in both, 8 is in A, 9 is in both, and 10 is in B. So now we have this set that's 1, 2, 4, 6, 7, 8, and 9. So if we want to take our complement, it's going to be all the values that are not in A union B, but are in our universal set. So we say, so A union B complement is equal to the values not in A union B, but are in the universal set U. So if we look at our universal set U and we look at our A union B, we see that the only values missing from A union B that are in our universal set U is just the values of 3 and 5. So we say that a complement of A union B is the set of 3 and 5. Then lastly, we have here A complement union B. So first thing we want to do is find A complement, because we know what A is and we know what B is, but we do want to find A complement because we don't know that right away. It's not given to us in our problem. So let's solve for A complement. So we know that the value of A is 1, 4, 7, 8, 9. So now we just have to find all the values between 1 and 10 that are not 1, 4, 7, 8, or 9. So we say that A complement can't contain 1, but it can contain 2. It can also contain 3. It cannot contain 4 because 4 is an A. It can contain 5. It can also contain 6. It can't contain 7, 8, or 9 because that is in A. And it can contain 10. So we have that A complement is the set of 2, 3, 5, 6, and 10. So now that we know A complement, we want to take the union with B. So all we need to do is look at the values that A complement has and B complement has and the values that they share. So we say we want the values of A or B or both. So when we write out our sets, once again, we always kind of want to go in increasing order. So let's start with our lowest value. It's going to be 2. Next value is going to be 3. Then we'll have 5. Then 6. Then 7, 9, and 10. So that is what we got for A complement union B. So it's very important to know the difference between union and intersection by far. And then really just focusing, if you have parentheses, focusing on what's inside the parentheses, or if you have some sort of value with a complement, maybe find the complement first. You just basically trying to make it as easy as possible on yourself. All right, then section 7.2 is going to be all about applications of Venn diagrams. So we touched on Venn diagrams in section 7.1, but now 7.2 is just going to use all the definitions that we just learned, and we're putting them in Venn diagrams. So for figure 5, we have 3 different Venn diagrams here. And for figure A, we have this picture here. So we have overlapping circles. We know 3 looks like it's going to be the intersection. 2, 3, and 4 would be the union. What we see here, figure 5A, we see we have 2 sets, A and B, colored by what they are. So A is blue and B is pink. And then the elements they share, which is 3, and the elements not included in either, which is going to be everything in this box that's considered 1. Then for figure B, we have 2 different sets, not overlapping at all. We see that A and B colored by what they are, so A is blue and B is pink. And the elements not included in either, which is going to be 1. So you see the elements in 2 are in A, elements 3 are in B, elements 1 are in neither. And for part C, we see A is inside of B, where A is pink and B is blue. And these represent the elements in A also being in the elements of B, but not containing either. So this Venn diagram represents a subset, really. So when we're looking at this, we're seeing that A is a subset of B since it's contained within B. And then anything outside in this white area is considered not neither of them. All right, so in the previous section, we used N of A to indicate the number of elements in a set A, or any example set A. We can also use it for this rule, which we have the union rule for sets. N of A union B is equal to N of A plus N of B minus N of A intersect B. So when A or B are disjoint, then N of A intersect B is just equal to 0, since they don't share any elements. So the union simplifies to N of A union B is equal to N of A plus N of B, or since we know that N of something means the elements in, so the elements in A union B is equal to the elements in A plus the elements in B. So another word of caution, we have this union rule is only valid when A and B are disjoint. When they're not disjoint, we use the official rule. By official rule, we mean this official rule. So this little kind of cheat rule with N of A union B is equal to N of A plus N of B, that only works when we have disjoint sets. But if they're not disjoint, we use our official rule. All right, on to example 3. So we want to use the union rule to solve the following problems. For part A, we're going to let N of A be equal to 4, N of B be equal to 10, and N of A union B equal to 11. We want to find N of A intersect B. So normally, with our union rule, we have N of A union B is equal to N of A plus N of B minus N of A intersect B. So what we have here in our problem, we are given N of A union B, we're given N of A, and we're given N of B, and we need to solve for N of A intersect B. So we can say we know the union rule is, let's just rewrite it, N of A union B is equal to N of A plus N of B minus N of A intersect B. All right, so we know this union rule, so let's plug in our values. If we do that, we're going to get 11 is equal to 4 plus 10 minus N of A intersect B, which we're trying to find. Then we see here this is 11 is equal to 14 minus N of A intersect B. So we can subtract 14 on both sides, and then multiplied by -1 in this case, since it would be negative. But essentially what we're going to get is that n of A intersect B is equal to 3. So that would be that value. Now for part B, we're going to let n of A be equal to 7, n of B be equal to 12, but A and B are disjoint sets. Find n of A union B. So A and B are disjoint sets, which means that they don't share any elements. So we can use our property to say that when A and B are disjoint, then n of A intersect B is equal to 0. So the union simplifies to n of A union B is equal to n of A plus n of B. So we can use this property for part B. So we say we know our values of n of A and n of B, but they're disjoint. So n of A intersect B is equal to 0. So let's use our property to get, and we essentially just get n of A union B is equal to n of A plus n of B, or n of A union B is equal to 7 plus 12, so we get that n of A union B is equal to 19. All right, so moving on to example 4. We want to shade the following Venn diagrams to show, for part A, we have A complement union B. So now we're just shading Venn diagrams. We don't actually know the elements inside of these sets. We just have Venn diagrams and our expressions. So let's just start by shading in A complement. And then we'll shade in B, and then we know that our answer is going to be the union, or both. So if we want to shade in A complement, we'll say this yellow color is A complement. So A complement, any value that's not an A. So this means pretty much our entire rectangle that's not contained in A contains B. I just don't want to color over it. All right. So now we've colored in A complement. Now we want to color in B. So we see B is going to be this value that they share. But also our middle part here. So yeah, I'll color that in too. So we say the little blue square is B. So we have shaded in A complement. We have also shaded in B, and we know that our union is going to be what they are combined. So we have shaded in our Venn diagram. Now, if you'd like, you could go over it in one single color to show that you understand, or to show that it's just one single color, but you should end up getting an answer that looks like this. All right, so then for B, we have A union of B union C complement. So now we have 3 different circles on our Venn diagram. So let's pick some different colors. Pick green. So we want to find, remember we want to find our values of B union C complement first. So if we say B union C, it's going to be all of our values in B and all our values in C. But we want the complement, so what we have to do is color in everything. So if we do that, it's going to be everything not in B and C. So we see here, we start filling in all around. We do color in A. Since it's not B or C. So we say this color is B union C complement. So then we can use a separate color, and we're saying A union with what we already colored in. So we know that A is just going to be all the values in A. So we can color in all of our elements in A, which we know is our circle. So we've colored in our circle of A, and we have colored in our sections of B union C complement. Since it's a union, we're considering both areas, or all areas that are shaded in. So our Venn diagram is now shaded in. Like I said before, you can pick one color and have it all shaded in. When you do these problems on WebAssign, that's what you'll do. You'll just fill in the areas and it'll have the same color. So you can pick one color, but we have shaded in all the regions. All right, and for example 5, we want to use the Venn diagram to determine if the statement is true or false. So this essentially is just telling us that we can use this Venn diagram to determine if the statement is true or false. The shading in of the Venn diagram actually doesn't matter for the question. It just means that we can use the Venn diagram to see if this statement is true or false. So we always want to start first with our parentheses. So we see, let's do this. So we're going to say A union B complement intersect C are going to have these colors, and then C intersect with A complement intersect B complement will have these colors. So as we're coloring them in, we'll know what they are. So we'll give this blue color to A union B complement. So if we're thinking about A union B, we know A union B are all the elements in A and all the elements of B and all the elements of both. So essentially, we're just coloring in anything that's not A or B or both. So we're pretty much just going all around A and B. We're coloring in C here, a little circle around C. So much coloring, so fun. The tools you'll have on My Math Lab is going to be a lot easier because you can just click once and it will be all filled in. All right, then let's pick this purple color here, and this is going to be C. Now remember, our value of C is just any value we have in our whole circle of C. But what we're asking for in this case is we're finding the intersection for the values that are in both. So we're looking for the areas that are purple and blue. So when we look at our Venn diagram here, it looks like our area is going to be right here. So let's give it one more color. Come on. And let's give this orange. And we'll say orange is the whole thing. So we'll say orange is A union B complement intersects C. So we're going to erase our coloring. We know which area is supposed to be our value. So we know it's going to be this area here. So this is the area that we came up with. Now what we need to do is focus on the other side and see if we come up with the same area. We're going to be using different colors, so I'm not going to leave this shaded in. I'm just going to outline it. So I'm going to erase it, and instead we're going to outline. This is to signify that this is the area that we want. So let's pick some different colors. So let's start with green now. And now we're going to pick our parentheses first, which is going to be A complement intersect B complement. So what we're looking for are the areas not in A and not in B. So if we're looking for the areas not in A and not in B. So when we color in this value, we know that our universal set is obviously not going to be in A or B, or A and B. C is also going to be not in A, not in B. So we see we're going to end up filling in our diagram. It's going to look like this. Well, we're pretty close. We have the area that we want shaded in already. And we also have all the other area. So we can pick another color, navy. We'll say this navy color is going to be C. And now we have C, or yeah, we're going to color in our whole area of C before I get too far ahead of myself. So we color in our whole area of C. And what we're looking for is C intersect with our areas of green. So we want to see where our areas of green and blue overlap. So if we look at a picture here, we can see that our areas of blue and green overlap in the same area that we had outlined in orange. So let's pick this pink. Since we obviously see that these areas are going to be equal to each other, we say that pink is going to be A union B prime intersects C, and C intersect A prime intersect B prime. So we can erase all of our shading that we did, and we see that we get this area here. So since using our Venn diagrams, we had shaded in the exact same spots for both of our expressions here, we see that they are equal. So we can say by using our Venn diagram, we get that these expressions are equal. All right, so that concludes our little review of section 7.2. So which is all about Venn diagrams. All right, in section 7.3, we're moving into probabilities. So we have a probability. An experiment is an activity or occurrence with an observable result. Each repetition of an experiment is called a trial. The possible results of each trial are called outcomes. And the set of all possible outcomes for an experiment is called the sample space for that experiment. So an example, in tossing a single coin, the only outcomes are going to be heads or tails. So the sample space, or S, would be S is equal to the set of H comma T. So we have two options, two outcomes. An event is a subset of a sample space. So an example of the sample space for tossing a coin is S is equal to the set of H comma T, or heads and tails. Then one element, which we'll signify as E, is equal to, we can say, heads, or the set of H, which represents the outcome, heads. Then if an event includes the entire sample, that's called a certain event. And it's called a certain event because if it contains all the elements that are in the sample space, then they're equal. So that event is going to happen 100% because every element in that event is also in the sample space. Since events are sets, we can use set operations to find unions, intersections, complement, and complements of events. So we can see all the different set operations that we used in our last sections are also useful in events. So we have set operations for events. Let E and F be events in a sample space S. Then E intersect F occurs when both events E and F occur. E union F occurs when E or F or both events occur. And then E complement occurs when E does not occur. Two events that cannot occur at the same time, like rolling an even and odd number with a single die roll, are called mutually exclusive events. Mutually exclusive events, we say if events E and F are mutually exclusive, then E intersect F is equal to the empty set. So E and F are just signifying in this case that they are two outcomes that cannot occur at the same time. Also, we see that with the intersection of E and F, we're going to get the empty set, which is the same thing as saying disjoint sets. So mutually exclusive events are just disjoint sets, which is another word for it that we use when we're speaking about events. For sample spaces with equally likely outcomes, the probability of an event is defined below as the basic probability principle. Let S be a sample space of equally likely outcomes, and let event E be a subset of S. Then the probability that event E occurs is the probability of E is equal to the number of elements in E divided by the number of elements in S. So for any event E, we see that our probability of event E is always going to be between 0 and 1. If we want to think about it in percentages, that would be a 0% outcome and a 100% outcome. So you can't have less than 0, can't have more than 1. In many real-life problems, it's not possible to establish exact probabilities for events. So we make useful approximations by drawing on past events. So we use data that we've gathered in the past to create approximations or estimations for the future. These are going to be called empirical probabilities. All right, so that was a lot of information, but let's move on to our example 6 so you can put some of this in practice. For example 6, all we want to do is write a sample space for each given experiment. For part A, we want to write a sample space for a day of the week is chosen to have a meeting. Now we know we can choose any day of the week. So our outcomes are going to be each day of the week. So we write our set. We say Monday, Tuesday, Wednesday, Thursday, So our set in this case is just going to be every day of the week. We can choose any day of the week to have this meeting. So our set is every outcome or every option. Now for part B, we have a red face card is chosen out of a single deck of cards. So we know that when we have a single deck of cards, there's 52 cards, 26 cards are red cards, or 2 suits of 13 are red, and then we know that there's 3 face cards in each suit. So if we're only considering 2 suits, and there's going to be 3 red face cards in each suit, then we know we have 6 outcomes, or 6 different outcomes of pulling a red face card. So when we end up writing this out, we just want to list all the different options. So we can start with the suit hearts. So we can say King of Hearts, Queen of Hearts, and Jack of Hearts. All right, so that's 3. Now we have 3 more red face cards that are not in the suit of hearts. So we know this is going to be diamonds. So we have King of Diamonds, Queen of Diamonds, and Jack of Diamonds. So our set was the 6 different options of red face cards in a deck. Then lastly, part C, a die is rolled twice and the results sum to 9. So we're seeing we have 1 die and we're rolling it twice. So when we write these, we're actually going to write them in comma separated subsets, essentially. So when we write this, we're going to write them as an ordered pair. So we know that the die is being rolled twice, and the results are going to sum to 9. So we need to think of all the different ways that our values can sum to 9. And in this case, order is going to matter. Since we know that if we roll 1 die gets 1 number and 1 die gets another number, we know that we have to have the order, because you can say, well, this die is going to roll this number and this die is going to roll another, but we also want to consider the other factor of that. It'll make more sense in a second when I write it. So let's say our first die rolled a 6, then our second would have to roll a 3. Then let's say our first die rolled a 5, then our second die would have to roll a 4. Because remember, we're thinking about these summing to 9. Now we have 6 and 3 and 5 and 4, and if you think about it, these are the only combinations we can get that will sum to 9. But now we consider the opposite way, because we only considered in this case our first die rolling either a 6 or a 5. But our first die can also roll a 4 or a 3. So now we switch our values. So we say 4 and 5 and 3 and 6. And that is our set. So we have all the different options in all the different ways that they can appear. All right, then moving on to example 7, we have the following table gives the number of club members per major. Find the probability a randomly selected student is a biology major. So we see here we have this list of students. We have 7 students that are English majors, 8 students are biology majors, 11 students are education majors, 12 students are psychology majors, 14 students are communication majors, and 9 students are engineering majors. So our event in this case is that a student is a biology major. If we're randomly selecting from any one of these students, our event would be getting a biology major. So if we want to go back up to our basic probability principle, we want to remember the probability of our event. So we want to find the number of elements in our event and divide by the number of elements in our sample space. So our sample space is equal to the total number of club members. So we just need to add up all of our different club members. So we have 7 English majors, 8 biology majors, 11 education majors, 12 psychology majors, 14 communication majors, and 9 engineering majors. So we just need to add all of these up, and when we do, we end up getting 61. So there's 61 club members. Say, or n of s is equal to 61. And let's put sample space s. There we go. So now we have our number of elements in our sample space, which is 61. Now we just need our number of elements in our event. And we say E is equal to randomly selecting a biology major. Or the elements in E is equal to 8, since there's only 8 biology majors. So using our formula for basic probability principle, you can say using our formula, we get the probability of selecting a biology major is equal to n of E divided by n of S. And this is going to be equal to 8 divided by 61. We can put this in decimal form if we want. In that case, we would get 1.311. This is also like saying 13.11%. Okay, so that is how we would use our basic probability principle in trying to see if we can randomly select a biology major out of all of our club members. All right, so on to our very last section, section 7.4. We're going to be using a lot of our probability definitions and just all the definitions in general that we've learned before the section. So by manipulating the union rule, we can get the union rule for probability. It's pretty much the exact same thing. It's just now we have probability instead of number of elements. So we have the union rule for probability for any events E and F from a sample space S. The probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersect F. Word of caution, the rule P or the probability of E union F is equal to P probability of E plus probability of F is valid only when E and F are mutually exclusive. Or like when we learned our original union rule, when they are disjoint sets. So when E and F are not mutually exclusive, we use the original rule. When they are mutually exclusive, we can use kind of like this cheat rule. So by definition of E prime for any event E for a sample space S, E union E prime is equal to S. So this means all of our elements in E and all of our elements not in E. It's going to be equal to our sample space. And E intersect E prime is equal to the empty set. And that's because they're mutually exclusive events since they can't occur at the same time. This shows that E and E prime are mutually exclusive. So the probability of E union E prime is equal to the probability of E plus the probability of E prime. But since we know that E union E prime is equal to S, we get that the probability of E union E prime is equal to the probability of E plus the probability of E prime, and that's all going to be equal to 1. Or we can derive our complement rule. And our complement rule states that the probability of E is equal to 1 minus the probability of E prime, or the complement of E, and the probability of E prime is equal to 1 minus the probability of E. So it's going to be very useful when you get the probability of an event or the probability of the complement of an event. Sometimes probabilities are given in terms of odds, a comparison between P of E and P of E prime. This basically just means that odds in favor of an event E are defined as the ratio of P, or the probability of E to the probability of E prime, or probability of E divided by the probability of E prime. The probability of E prime is not equal to 0, because then this whole equation would not exist. All right. So then if the odds favoring event E are M to N, then the probability of E is equal to M divided by M plus N, and the probability of E prime is equal to N divided by M plus N. So this is like if your odds in favor of event E are 9 to 11, then your probability of E is going to be N divided by 20. Or your probability of the complement of E would be 11 divided by 20, because you want to add your M and N and have that in your denominator. All right, so then a table listing each possible outcome of an experiment and its corresponding probability is called a probability distribution. The assignment probabilities can be made on an empirical basis or theoretical reasoning, provided that it satisfies the following conditions. So this is basically just saying that you can have a probability distribution as long as it follows the conditions. So we see here properties of probability. We let S be a sample space consisting of n distinct outcomes. We call these S sub 1, S sub 2, up to S sub n, however many outcomes. An acceptable probability assignment consists of assigning to each outcome, S sub I, so that just means any outcome, a number P sub I, or the probability of S sub I, according to these rules. So number 1 being the probability of each outcome is a number between 0 and 1 inclusive, so it can be 0 and it can be 1 or anything in between. And number 2, the sum of the probabilities of all possible outcomes is 1. So we have the sum of all the probabilities equal to 1. So basically we say that we can have a probability distribution as long as each one of these outcomes is satisfied. All right. Then for example 8, we have a survey revealed that 57% of people use Netflix, 32% of people use Hulu, and 29% of people use Netflix and Hulu. What is the probability that a person uses Netflix or Hulu? And we want to express this as a percentage. So what we have here is we have that a certain amount of people use Netflix, a certain amount of people use Hulu, and a certain amount of people use both. Now we want to find the percentage of people that use one or the other. So if we're thinking about this, we think, okay, we want to use the union rule for probability. So we say, I'm going to zoom in a little bit here. We can use the union rule for probability. Since we want our final answer as a percentage, we'll just leave our values in percentage form. Basically just meaning that we're not going to put them into decimals. We'll just leave them as whole numbers and just remember to add on our percentage sign at the end. So we're going to let n be equal to Netflix. I should probably capitalize it. Netflix. And h be equal to Hulu. Then we get that the probability of Netflix or Hulu is equal to the probability of people that use Netflix plus the probability of people that use Hulu minus the probability of people that use both. And we know which one of these probabilities. We say that the probability of people using Netflix or Hulu is going to be equal to probability of people using Netflix, which is 57, plus the probability of people using Hulu, which is 32, minus the probability of people using both, which is minus 29. Now we can add these values up, and we end up getting that the probability of people using Netflix or Hulu is equal to 60, or 60%, since we know that we left this in percentage form. So we say 60% of people use Netflix or Hulu. All right, then finally, our last example, we have the following table gives a future year's projected company workforce probability distribution. This is by age and gender. So we have our table here, we have age, then we have male, female, and then we have our total. So we see here that since this is a probability distribution, just to make sure that it satisfies, we see that each probability is between 0 and 1. And then we see when we add up each of these values, they're all equaling to 1. And we add up our total probabilities. So they satisfy our conditions, and this is a valid probability distribution. So for part A, we want to find the probability a randomly selected worker is male or above the age of 36. We just write 36 plus. Our ages are 18 to 36, 36 plus. So if we want the probability that the randomly selected worker is male, or, the keyword being or, over the age of 36. So we want to find the union using the union rule. So we want to use the union rule to find the union, or the probability of the union having a male or a worker over the age of 36. So when we write this, we can say the probability male or 36 plus is equal to the probability our worker is male plus the probability our worker is over the age of 36, and then we're subtracting the probability that our worker is male and 36 plus. Now luckily we can find all of this information in our table. So we know our probability of our worker being male is 0.496. So we can rewrite this. So probability of our worker being male is 0.496. Our probability of our worker being over the age of 36 is 0.671. And our probability that our worker is male and above the age of 36 is going to be 0.314. So now we just want to calculate this value. And we get that the probability of our worker being male or above the age of 36 is going to be equal to 0.814. 853. Or we can say 85.3% if it asks for a percentage. If it doesn't ask for a percentage, probably just leave it in decimal form. All right. Now for part B, we want to find the percentage that our worker is female or 18 to 36 years old. So we're pretty much going to do the exact same thing. So we say once again, we want to find the union, since we see this keyword or. So once again, we want to find the union, so we'll use the union rule. So we want to find that the probability our worker is female or ages 18 to 36. So we want to find the probability that our worker is female plus the probability our worker is 18 to 36 years old. And then we want to subtract the probability that our worker is female and 18 to 36 years old. So we know these values, it's in our table. We see the probability of a worker being female is 0.504. So we can rewrite all of this. 0.504 plus the probability of a worker being 18 to 36 is going to be 0.329. And then remember, we want to subtract the probability of our worker being female and 18 to 36, which we see is going to be this value of 0.147. So if we calculate this value, which I highly recommend that you do, we should end up getting 0.686. Or if we put this in percentages, it would be 68.6%. Once again, only put in the percentage if it asks for the percentage. Other than that, you pretty much just want to leave it in decimal or fraction form. All right, and then lastly, our last question here is we want to find the probability that our worker is female and above the age of 36. So we know this is and, so we know our union rule, but what we don't need to do, or sorry, we know that this is the intersection since it's both, which we could use the union rule if we wanted to, but we don't need to because we have it in our table. We see that the probability that a worker is female, and above the age of 36, and we just follow in our table and we see the value is 0.357. So we didn't even need to use a formula for this part. We know it is just what we have in our table. Oh, come on, there we go, froze up. So we can say we can easily read this from the charts. It is 0.357. We say, you know, or 35.7% if you wanted it in percentages. All right, so that concludes the end of our Chapter 7 review. So please don't forget to take your quiz today as well. There's also a review session that the Math Center is holding, so I highly recommend you attend that there as well. So If you have any questions or concerns or anything, you can feel free to email me, pop into my office hours, or you can submit an anonymous question to our anonymous homework form. So I will see you all virtually later, and good luck on your test.